Downtime is expensive. A recent study found downtime in the food and packaging industry averages 25 hours a month, costing $23,000 an hour on average. Contrast that with the automotive industry that's closer to 30 hours of unplanned downtime each month at over $100,000 an hour. Predictive maintenance can play a crucial role in not only reducing costs, but also boosting productivity at a time when manufacturers need all the help they can get to meet the demands of ever-changing industry. But where do you start? Predictive maintenance is a big topic and can be intimidating for manufacturers just starting down their Industry 4.0 journey. Condition monitoring is a great first step and can reduce unplanned downtime and really lay the framework for a predictive maintenance model. Condition-based monitoring is a maintenance strategy that monitors the actual condition of an asset prior to deciding what maintenance needs to be performed. It's different from time-based maintenance or preventative maintenance. Condition-based monitoring dictates that maintenance should only be performed when certain indicators show signs of decreasing performance or upcoming failure. These indicators are easily measured with inexpensive sensors. Vibration, temperature, humidity, pressure, flow, energy monitoring, as well as advanced IO-Link sensor metrics are all examples of condition monitoring. However, in the last couple of years, we've really seen the emergence of condition monitoring sensors. These are devices designed specifically for these kinds of initiatives. They can provide vibration analysis, telling us the velocity. This tells us whether a motor is going to be unbalanced or misaligned. Typically, these are the kind of defects that you can feel. Or tell us acceleration. This notifies us of a bearing issue or lack of lube. These are typically the kind of defects you can hear. We get this analysis on vibration on multiple axes, so X, Y, and Z. So overall, it's a very powerful tool. We can also pull metrics like the mean, showing the average acceleration over time, standard deviation, which shows us the variation of that acceleration. Crest and skewness describes the curve and symmetry of that wave, while kurtosis shapes it out and tells us how close to a bell curve we are. This is all an effective tool for helping understand your asset's performance. We see this on pumps, presses, older robots, really any kind of motor that's critical. And as an added bonus, these sensors also give and provide temperature data, so knowing if a pump or device is overheating prior to failure. Most condition monitoring initiatives include a sensor like this, as well as incorporating other metrics, like monitoring pressure and flow. Sometimes advanced sensor metrics available over IO-Link also provide feedback that's useful in condition monitoring initiatives. Examples of IO-Link sensor metrics might be a photoelectric sensor that provides notification as it starts to get dirty. That sensor is still seeing the part, however, the amount of light being received back is slowly dropping as the face is getting dirty. That sensor can send notification that it needs to be cleaned, still providing an output to the PLC that it's sensing the part, however that light is slowly dropping and hey, someone come clean me. Or an inductive prox that isn't mounted correctly that's being used as a hard stop. With IO-Link, that sensor can let the system know that it's being used as a hard stop and alarm out to maintenance. Over time, being used as a hard stop will cause premature failure, potentially causing unplanned downtime. We can also easily incorporate energy monitoring into these initiatives. Knowing energy consumption allows us to optimize machine performance. Reach out to NEFF and let our team sit down with you to discuss how condition monitoring can help.